Okay, so we can start. Yeah, so I think I want to recall some stuff that we did before. Also, yeah, maybe give more examples. So let me recall. What we did last lecture. One of the things we did was for any discrete group gamma and any A module, any gamma module. A, we defined this group HI of gamma with coefficients in A for I equal to 0, 1, 2, 3, etc. I mean, this word discrete group, you have to come to terms with it. It's totally unnecessary to say that. When I say discrete group, it means that I don't use any other structure because your group may have somewhat extra structure, maybe a topological group, maybe a Lie group. Then I won't use those structures. I'll just use the group structure on gamma, and that's it. However, it's usually not very useful to use this concept for Lie groups or topological groups, unless you have some good reason, which you can. But in general, this is for when we say discrete, people have some sort of groups like which are maybe countable groups, this sort of things they have in mind usually. But still, you can use it for Q, for example, with addition, which is a countable group, but it's not discrete as a topology, which is not discrete. So anyhow, so we have this, and then in particular, we saw that H0 of gamma A is just A gamma. It's the subgroup of invariants of gamma invariant elements. Invariant elements in A. So we can also take a special case. This is an important special case, gamma equal to Z with trivial action. Then this gives us this group's HI of gamma with coefficients in Z, right? So we get this group HI of gamma with coefficient in Z. So now I can define a group has finite cohomological dimension. So yeah, I had this definition last lecture, but it was not a quite correct definition. There is a nuance that I have to pay attention to. So I'll mention it. So we say that gamma has finite cohomological dimension. If first of all, HI of gamma Z are all finite rank, because these are abelian groups after all, right? These are all finite rank abelian groups, or finite rank for all I. And they are actually 0 for I large enough. HI of gamma Z is equal to 0 for I larger. If you go, so in that case, then we define the Euler characteristic of gamma, I of gamma, we defined it to be equal to, by the usual formula, sum minus 1 to the power I. Now I can take the rank of these groups, which are finite rank. So these are some integers. I can take those integers. So I just put rank of hi of gamma z over I. But then they turn out also to be related to dimensions of these groups when we take coefficients in Q. So this is equal to sum minus 1 to the I dimensional hi of gamma with coefficients in Q. So these are vector spaces, finite dimensional vector spaces, and now we are taking the dimensions. But rank is also an intuitive concept for abelian groups. Okay, so that's the thing. Now the point of confusion is, you see, the tendency is to define finite rank to say that these guys are finite dimensional for all I, and they are 0 for I large enough. But then something goes wrong if gamma is a finite group, and that's for the following reason. I give this as an exercise in group cohomology, actually. Exercise is the following. Show that if gamma is finite, a finite group, then actually hi of then hi of gamma q, in fact, with coefficients in any module over a field of characteristics 0. This is equal to 0 for all I positive. So if you go to positive to 0 characteristic, if you have a finite group, then these cohomologies are all 0 for in positive degree. It's a very nice exercise in group cohomology to prove that you have to define some averaging operator or something. Yeah, some norm operator or something. It's a very interesting exercise. Okay, so then if I just take this vanishing of these guys as finite, finite cohomological dimension, then finite groups would fall into this category as. But in fact, finite groups have non-zero cohomology in all dimensions if you work over Z. So finite groups don't have finite cohomological dimension. So that's a confusion, right? So it's just here, but finite groups typically don't have finite cohomological dimensions. Don't have finite cohomological dimension. In fact, we looked at example Z2 even. For this, we saw that it has cohomology in all dimensions. In fact, it has periodic cohomology. Okay. So this is a fine point one has to pay attention to, right? So Okay. Yeah. I mean, an example of this we looked at, so here's another example we looked at was if gamma is equal to z, then we check using the universal covering, right, business, that in fact hi of z with coefficients in z, yeah, this is actually equal to 0 for I bigger than 1. We checked it last lecture because we showed that it has Bz is equal to R, and this guy has cohomological potential. I'll find the cohomological potential. Oh, no, he said it's S1. Yeah, sorry. Yeah, it's S1. Ez is R. Right. And this has cohomological dimension exactly 1 because the dimension 0 and 1 is non-zero, and then in other dimensions are just yeah, after. Okay. All right. So yeah. Now, okay. So then we have to extend this definition to kind of more general case. So we looked at an extension of this concept, which is defined for we called it almost finite cohomological dimension. Right? So definition was that gamma has almost finite cohomological dimension. We saw that if the definition is that if there exists a subgroup gamma prime inside gamma, such that it's as finite index, and gamma prime itself has finite cohomological dimension. I'll just write it like this: finite cohomological LCD. Okay, and then in this case, we find the Euler characteristic. Was defined to be Euler characteristic of gamma, was defined to be equal to Euler characteristic of gamma prime, which exists by this first part, this finite cohomological dimension, and then be divided by index. I mean, so for this to make sense, you have to make sure that two things. First of all, if you pick another subgroup which also has a finite cohomological dimension, has finite index, the two definitions coincide. You have to check that. That can be checked. And also, we have to check that if it happens that actually gamma itself has finite cohomological dimension, and you pick a subgroup like that, the two definitions coincide again. So you have to prove some multiplicative formulas. But these are the kind of things that you do in courses about group cohomology and stuff, homological algebra stuff. Okay. So, and then we looked at the example, order of gamma less than infinity, then it's Euler characteristic. So this number, of course, is not integer anymore. And in fact, there is a drastic case where it's finite group. And in this case, it happens to be 1 over order of gamma. So the characteristic could be any inverse integer, positive. But it could be negative as well, so we'll see that. Now, so this is example 1. I believe we looked at part of example 2 as well, so but I'm going to do example 2 now. So this example is very relevant because it already proves a special case of the theorem that we want to prove. So example 2 is gamma is SL2Z. This is the set of all integral matrices such that AB minus BC is equal to 1 and A, B, C, D are integers. It's an infinite group. It's a discrete group, it's countable, and yeah, it's a very important group. So this, we want now to show that this has almost finite cohomological dimension. And gamma has almost finite cohomological dimension, or is of almost finite cohomological dimension. So yeah, the syntax, I'm not sure what's the right syntax. Okay. Now, question, yeah.
Independence on gamma prime in the definition of the Euler characteristic.
Yes, that's good.
That should only be true for finite gammas, right? Because if gamma was infinite, then we can still take the identity group or the trivial group to be the subgroup gamma prime, and it will have the.
That's not a finite index.
Sorry, fine.
There's a second condition that gamma prime has to be finite index. That's a condition. Because we are dividing by that. So let's see. Okay, so now this guy. Now, first of all, let us notice that gamma itself is not of finite cohomological dimension. Gamma is not of finite cohomological dimension. And the reason for this is that, you see, we saw that these finite groups are kind of bad in this regard because they have cohomologies in all dimensions. And that's kind of counterintuitive, right? Because a finite group, like a group with 4 elements, it has cohomology in all dimensions. It looks like an infinite dimensional object all of a sudden. That's very counterintuitive. But it is true. And in fact, not only that, if you have a group that has a finite subgroup, this makes that group to have cohomology in all dimensions. So proof of this, gamma has a finite subgroups. Again, this implies that gamma is of infinite cohomological dimension. Gamma has infinite cohomological dimension. So what finite subgroups we can find here? Let us write down some finite subgroups. I can write a subgroup of order 4. Yeah, so here, let S be this matrix 0, -1, 1, 0. I mean, this is the famous transformation, which is the in Euclidean geometry is called the polar transformation. So S of Z, essentially like that, but not quite. S of Z equal to -1 over Z. As a Mobius transformation is this one, right? Okay, now this guy generates a group of order 4. So we can just check that S4 is identity, and it's a cyclic group of order 2. Okay. the group generated by S is Z force. It's a single group for the form.
Well, one question about example once is there a converse to it? Like would the Euler characteristic of the integers be zero in the limit, or
Euler characteristic of integers?
yeah, would it tend to zero?
Yeah, it is zero. Yeah.
Oh, okay. So it's um it can still hold it in the limit when the index goes to infinity, but not always, I guess.
I'm not sure I understood the comment.
I guess like the premise is that the index of a subgroup or of gamma itself be finite, but
Yeah, exactly.
um
Yeah.
but it still works in the limit. Oh, all right.
Yeah. Okay. Right.
So,
Uh, okay. So we have this subgroup. Now, in fact, there is another element which is this one. So there is this thing. I just write it as T, but that's okay. We just take this element 0, -1. Ooh, yeah, 0, -1, 1, 1. So this guy has order 6. You can check. SD to the power 6 is the identity. So the group generated by SD is a cyclic group of order 6. You can, in fact, list all finite subgroups of SL2Z. I mean, that's an important point, but I mean, at least we have these two finite subgroups, and this finite subgroups shows that then this group SL2Z does not have finite homological dimension. This, you know that. Okay. You can take any of those two as providing your finite subgroups. Okay. But then we want to show this, that F has almost finite homological dimension. So we have to produce some gamma prime inside gamma, which has finite index, and gamma prime itself has finite homological dimension. So then we have to find some gamma prime inside SL2Z. Where is notation? Yeah, just so we define gamma prime to be the group generated by these two elements A and B, where A is this element, 1, 2, 0, 1. Yeah. So if you want, this is like A of Z. What is it? It's like Z plus 2 divided by 1, which is Z plus 2. So it's translating by 2 to the right as a Mobius transformation. Yeah. And B is the following element 0, okay, sorry, 1, 0, 2, 1. Yeah, so B of Z as a Mobius transformation, then is yeah, okay, 1, 2, 1B is 1, 0. Okay, yeah, it's 1 over 2Z plus 1.
That Z over 2Z plus 1?
Sorry.
Is that Z over 2Z plus 1?
I've got 1, yeah, it's Z over 2Z. Thanks, yeah. Z over. Yeah. That's a Mobius transformation, yeah. Okay. So we have got these two elements. They generate a subgroup. So now we are going to claim that actually this the group that these two guys generate is free group on two generators. So gamma prime is the free group on two generators. So free group function. Two generators is usually denoted by F2. It's a very important group. So gamma prime isomorphic to F2. And in fact, these two elements. So what does this mean to be free group on two generators? Practically, it means that there's no relation between A and B. Okay, i.e., if e.g. something like A and 1, B and 1, A and 2, B and 2, and then A and K, B and K, things like that is equal to identity, right? Then all these guys are actually equal to 0. I mean, no relation exists except the most trivial relations always exist. A0, B0 is equal to 1. Then, okay, I mean, one thing we have to be careful here. We can have, for example, N1, 0, and then we can have A2, A minus 2 is also 0. So that's a counterexample to what I'm saying. So basically, this has to be precisely formulated, more precise than what I have over there. Yeah, so yeah. And maybe I should say that this is the shortest. I mean, maybe I put it the other way around. If I say mi and ni are different from 0, okay. So yeah, I want to this e.g. Okay, so e.g. in, put it this way, in an expression like that, if all of them are non-zero, then this implies that this expression, let's call it maybe G, then it implies that G is different from identity. There could be no relation among these things where where all these guys are non-zero. That's what free means. Okay, I mean, I can write it in terms of some mapping to isomorphism in this group, but this is the intuitive meaning of this being a free group on two generators. Okay, so I'll prove this soon. Okay, so far we have this free group on two generators inside here, and exercise is show that actually the index of gamma in gamma prime is 12, is definitely less than. So this has an index 12. You have to work with these elements of order 6 and 4 over there to prove this. And then these two things, I claim that 1 and 2 basically implies that gamma as almost finite homological dimension. Okay. Okay, so I will come back to this proof of that this is free group on 2 generators very soon. But this is an exercise. But now let us prove the claim. The claim is proved if you prove these two things. So now we want to compute the Euler characteristic of SL2Z. Right? The Euler characteristic of this group. So this is going to be equal to, by definition, the Euler characteristic of this free group on 2 generators, gamma prime, now divided by this index, which is 12. Right? So now the question is, what is Euler characteristic of F2? Right? So what is the Euler characteristic of free group on 2 generators? Okay, so now we have to compute this cohomology in all dimensions, right? And for this, we can compute the classifying space of F2, free group on 2 generators. So B of F2, the classifying space, as I discussed. B of F2 is actually is figure 8 duality. It's infinity. It's a bouquet of 2 circles. It's a bouquet of circles. And in fact, the E of F2, the E space is a tree, infinite tree, 4-valent tree. At each vertex we have valent 4. So this is following. I mean, it keeps going, right? And it's an amazing object if you think about it. It never ends, and it always expands. It's an incredible object. This sort of trees. Okay. Yeah. So F2 acts on this freely. This is contractible. F2 acts on this freely, and the quotient here is going to be this space, the bouquet of. Okay, so then what does so here this fact implies that HI of F2, the integral coefficients, is equal to, first of all, Z, if I is equal to 0, and this guy is Z2 has 2 loops, I equal to 1, and this is a one-dimensional object. It's 0 for I bigger than 1. Okay? So the Euler characteristic then is going to be equal to 1 minus 2, which is minus 4. Right? So the Euler characteristic minus 1. So, okay. So then this calculation can be finished. So Euler characteristic of SL to Z, in fact, is equal to minus 1 over 2. This is what it's negative, and it's a negative rational number, and yeah, so okay, right. So except for this exercise that I want you to do, I have to do this still to show you how to prove this. And that's not obvious. Here there is a famous lemma in group actions, which is called ping pong lemma. I use that to indicate the proof. Okay, so any questions? Yeah.
Here, can EF2 be thought of as embedding F2 inside R2, for instance, because it looks like when we have a word in F2,
it is
just rallying around.
EF2 exactly. EF2 exactly like the Cayley graph of F2 itself. Yeah, that's what it is. Yeah, we can label all elements of E of F2 by elements of F2 itself. Which if you go right, you have A. If you go left, you have A inverse. Up, you have B. Down, B inverse. And then you keep going on. And then you generate all words, which are words of F2. And the action is by left translation over that. So it's a very nice action. Yeah. So okay. Yeah. But I mean, these are very mysterious objects for me. These are very, very deep objects. Yeah. Okay, so yeah, let me tell you about this ping pong lemma. I want to keep this here. So proof of this statement. Okay. Yeah, use ping pong lemma. So we let SL to Z act on R2, but not by Mobius transformation, by as linear maps. Act on R2 by linear map. So in this case, then A, B, C, D, E, X, Y is like a usual matrix thing, which is AX plus BY over CX plus BY. You see, this is very different compared to Mobius action. Mobius action is completely nonlinear. It's crazy. It's very complicated. This is linear. Okay, so we know it acts on R2. Then we are going to designate two subspaces of R2. Let X1 be the set of all XY in R2 such that absolute value of X is bigger than absolute value of Y. And X2 set of all X and Y such that the absolute value of X is less than absolute value. Okay, so what are these domains now? Yeah. Absolute value of x bigger than absolute value of y. How does it look like? It means x2 is bigger than y2, so it means x minus y, x plus y. So the relevant things are here. Okay. This is x equal to y line, and this is x equal to minus y, right? So I believe here is x1, right? And the other one is x2. Because for this, we must have x2 minus y2 positive, so it means that x minus y, x plus y positive, so it means that either both of them are positive or both are negative. So x minus y to be positive, if x minus y is positive, we are here below, but then in that case, x plus y has to be positive as well. It means that we have to be here, right? Because x has to be bigger than minus y. So this is the one. And on the other hand, this is the other one. Are you in agreement, or this is high school problem? Can you verify this? Yeah.
Shouldn't x1 be half of the plane instead of 1/4, and same with
x1. This is x1. This is no, domain x1, x2. You mean
for instance, if we take the point 0, 1 on the y-axis.
0, 1?
Yeah.
I thought that the whole thing is x1.
But
No, this is x1.
I think x1 should be half of the plane,
Yeah.
not quarter.
Half of the plane. No. You see, if you are here, for example, right?
Yeah, then you are in x2.
Then you are
The shaded area is x1 over here.
Yeah, like the whole shaded area should be x1.
x1.
the whole x1 shaded area.
Yeah, on the left as well.
On left is also
Oh, on the left. Oh, okay, I see.
Yeah, this
okay.
total should be x1.
and the complement is x2.
The complement is x. Oh, okay, yeah. Okay, good. Yeah, I was too quick to. Okay, so this is x2, right? Okay, good. This is x2 and this is x2. Yeah. Okay, cool. Yeah, very good. Yeah. Okay, so these are the two formal exponents. And then now you can check that now for every G belonging to this group generated by A, now A is that element. By the way, you can show that these A and the groups generated by A and B are infinite cyclic groups. So in fact, you can compute AN to be this matrix is 1, 2, and 0, 1 for n belonging to. You can check that a to the power n is this matrix. So there's no relation. B to the power n is also that matrix.
2 to the power n, not 2n.
Huh?
Should be 2 to the power n.
Oh, it's 2 to the power n. Why? Why is it not 2 to the power n? I don't think so.
Yeah.
No, because yeah. And this is 1, 2, and 0, and then 1. So this immediately shows that you have got a cyclic group, infinite cyclic group in both cases. But for every G belonging to this group A, actually you can show that G of x1 is mapped to x2. So this is a pimple. G of x1 is inside x2 for every G belonging to A. And also G of x2 is mapped into x1 for every G belonging to. And this is belonging to B. It's the other way around. And then it is not difficult. So this is the ping-pong lemma in this case that actually it's just a paragraph argument that this implies that there's no relation between them. You can draw the contradiction if there's a relation by using this. Implies that is the free group on two generators. I mean, this ping-pong lemma is more general, but essentially it's something like this. There's some decomposition of the space that it has. Yeah. So this calculation of Euler characteristic of SL to Z is the genus 1 case of the result we want to prove for genus G now. So I will go to that one. Yeah. Yeah. Okay, so now we can go back to moduli space story a little bit. Okay. Maybe I understand it a little better. So what remains now to be told in this case? Yes. Okay, yeah. Right. So now I want to introduce this thing called mapping class group. This group. So let's assume you have a closed Riemann no, not Riemann, closed topological surface of genus G. Let sigma G be a closed smooth oriented surface of genus G. So let me no Riemann space, no Riemann surface structure. It's just a smooth structure. Okay. So no Riemann surface structure. I mean, let me put it, no complex structure. Let me put it, it's just a topological story, smooth story, same, no complex structure. Okay. Okay. So to this space, you can attach some groups. So what are these groups that we want to attach? I mean, first of all, there is this group of diffeomorphisms of sigma G. which is a group of symmetries of this object, group of diffeomorphisms of instead of all phi from sigma G itself, phi is a diffeom. It's a huge group. It's infinite dimensional. But I won't define what sense is infinite dimensional because infinite dimensional groups is kind of nasty subject. But definitely is a topological group. I mean, you can is an infinite dimensional topological group. Yeah, so an infinite dimensional topological group. Right. Okay. I mean, the topology, you can imagine how it's induced by compact open topology because it's a maps, so topology of mapping spaces. It's Hausdorff, but it's infinite dimension. Okay, it has some subgroup. This one, diff plus of sigma G. This is what we are going to work with. This is orientation preserving because this guy I said is oriented. Is orientation preserving things. So this is orientation preserving diffuse. Yeah. Okay. So, I mean, this guy inside diff sigma G, I believe, is of index 2. It's a subgroup of index 2 because if you have orientation reversing, you can multiply by some, I believe, from index 2, more or less. But this now has an interesting subgroup, which is the connected component of the identity. So, but I say diff plus is not connected. So the connected component of identity is an important subgroup. Denoted by D plus 1 of sigma G. This is the connected component of the identity. So what is it? This is called the group of diffeomorphism that are isotopic to the identity. If i.e. diff plus 1 is diffuse isotopic, right? So isotopic means that there's a path of such groups that connects it to the identity. If there exists t belonging phi0 equal to phi. I mean, we can say phi1 maybe equal to phi, and phi0 equal to identity. I mean, this phi t is a smooth in T family of orientation of difference. So if you want, we can say that we have this map now phi from 0, 1 to diff plus sigma G, right? Such that at one end is your diffeomorphism, at another end is your identity. So everything that can be connected smoothly or continuously is enough to imply the same is going to be this one. So this is an important subgroup connected component identity. And the quotient of it's normal subgroup also. It's can be shown. It's not difficult. Well, connected component of identity in any topological group is always a normal subgroup. So that's not. It's true for any topological group. So the quotient is the mapping class group. So definition.
Is it also open?
Sorry?
Is diff plus one open in diff plus?
It is also open. Yeah. So, yeah, because this is host open. So definition is that the mapping class group we can define it to be like gamma, I would say sigma G is defined to be this class of sigma G divided by it plus one of sigma G. Divided it plus one. Yeah. Okay, so now yeah, so this is now a discrete group, exactly because that's open and closed subspace. The quotient is going to be a discrete group, so is a discrete, in fact, countable group. So this is one of the most important groups in geometry, topology, mathematics. A lot of people spend their life studying this group. They live in this group completely. In the morning, they go there, they work, that's their construction site. In the afternoon, and maybe when they get tired, they go home, and the next morning, then they go there and work. That's how they spend their life. It's a very rich group. But I can't tell you exactly why this takes so much time. But let's keep that in mind. So we have three groups. We have diff plus, we have diff plus one, and then we have gamma, which is mapping class group. So here is one example, which I essentially did it, but okay, let me write it. For genus T equal to 1, this guy, yeah, gamma sigma 1 to torus. You just take a topological torus. This turns out to be actually equal to, I believe, PSL to Z. So this is SL to Z divided by its center, which is plus minus 1 identified, because the action is the same. So this is SL to Z divided by plus 1 identity. So this is the center of this group. You divide by the center. This one. So now I have to be careful. Is it PSL to Z or is it SL to Z itself? Okay, so I put a doubt here. It's either this or without P. I'm not 100% sure now. I have to check it out, think about it. I believe it is with P, but okay. Now, what it has to do with the moduli spaces of this story? The reason that this becomes relevant for our story is the following now. So let us recall we defined mg. So now I'm not taking any mark point just to make life easier without mark point discussions. So we define mg to be modular space of closed Riemann surface. So genus G was the set of all Riemann surface of genus G divided up to isomorphism by isomorphism. So this is all genus G Riemann surfaces divided by isomorphism. Right? Okay. So when we think of mg as this, we have the following things in mind. We have all these different Riemann surfaces around the world. Everyone has his own model. You can construct your own set. You can name your set differently. But then if they are isomorphic to each other, we consider them the same. So it's like a big category with all these objects in them and isomorphism. But we can focus on one surface and consider all possible complex structures on that surface. So that's okay. Alternatively, we can define fix a genus G surface without complex structure. As say we call it sigma G, like over there, right? And consider all possible complex structures on this sigma G. All possible Riemann surface structures on sigma G, right? Riemann surface structures on sigma G, right? Okay, so and then I can say, okay, and G is all Riemann surface structures on this fixed sigma G, but there may be redundancies here again, because now what happens is that I can take one of these diffeomorphisms, act on the complex structure, and produce another complex structure. So I have to divide by that. So mod out plus sigma G. So we just divide by the plus of sigma G. So now what we have to understand is how diffeomorphisms act on complex structure. Because what we are saying is that I have this Riemann surface, and I have this complex structure on the Riemann surface. How this diffeomorphism group of the, which has nothing to do with the complex structure. Diffeomorphism is a smooth story completely. How this acts on complex structure. In other words, if I have a Riemann surface structure here, how do I produce another Riemann surface using one of these D plus? So to understand that, we have now to understand what do we mean by Riemann surface structure or complex structure. So a natural choice, of course, is, so you have coordinate charts which are isomorphic to open subsets of C, and change of transformations are holomorphic. You can define the action of diffeomorphism group using that definition, but it's not very straightforward working with that. We can alternatively look at the following way of defining complex structures. So here again, I just say because so a complex structure on sigma G is fixed or is defined by a tensor field J. I mean, a smooth tensor field J belonging to endomorphisms of tangent bundle of sigma G such that J squared is equal to -1. I mean, so what does this kind of fancy language, but what does it mean? It means that you have a smooth family of endomorphisms of each tangent space at each point, right? So this is T sigma G at some point X on sigma G, right? This is the tangent space at one point. And what this map is, this map sends tangent space to itself, J squared is equal to -1. Well, J squared equal to -1 means that you can define multiplication by I on these things and fixing the complex structures. So in general, these things are called almost complex structure. But in dimension 2, namely complex dimension 1, it can be shown that there is actually no difference between almost complex structure and complex structure. They're the same. So, okay, so now if I have one of these J squared equal to -1 tensor field. So, by the way, this is in tensor language, maybe you're more familiar with tensor language. This J actually is a one covariant, one contravariant. So, or you can say J belongs to smooth section of the endomorphism bundle, which is the star of M tensor G. No, I mean, every way you think about it, it's the same. So now, if you think of complex structure as such J's, now you see how diffeomorphisms work or act on them. You just move the tensor because diffeomorphism act on tensor. Okay. So for any phi belonging to P plus, and for any J belonging almost complex structure, this phi star of J is defined. It is again a complex structure. Okay. So the only thing that remains is the role of orientation preserving, because it looks like here I can also take any diffeomorphism and I have a J, it acts on that. And then again, I get another complex structure. But this new complex structure won't be compatible. Yeah, I have to say that Riemann surfaces have a natural orientation. This is a feature of complex world. the complex world has natural orientation, but the real world doesn't have an orientation. That's kind of, it looks puzzling, but that's true. So in order to stay in the same orientation for sigma G, we have to take, yeah, orientation preserving maps or diffeomorphisms. So that's true. Now, in anyhow, so I think now this makes sense to us. And it's kind of should be now fairly obvious to see that this and that are the same. More or less. It's like we are bringing all possible complex structure on all possible Riemann surfaces over this space, but then all possible isomorphisms are reflected into all possible diffeomorphisms. So there's a little bit of categorical thinking or whatever, I don't know, helps here, but is this one. But now here is the trick that they use actually. Instead of dividing by this right away, so G, which is now Riemann surface structures on sigma G divided by this plus of sigma G, we are going to look at it. So this is kind of bad quotient space because it has a lot of fixed points and it's difficult. So people realize something like to do, it's better to do it this way. You first divide by connected component of the identity, which is better. So you say divided by the plus 1 sigma G. Right? You divide it by that. Then you divide this by the mapping class group, which is the quotient of this by the other one, by mapping class group. By gamma, that's my notation for mapping class group of sigma P. Mapping class. I mean, this looks very fancy, but in fact, that's what we use in combinatorics all the time. In order to count something, it looks very complicated. We do the counting usually in two ways. We go into something, we count up to some weaker relation, and then we take care of that relation later. So I don't know what there's a word for this in combinatorics. They say. Okay, I don't know. It's a very, very fundamental principle in counting, actually, which works here. So this space, by the way, the first space is called the Teichmuller space. Okay, so this is a notation. This one is Teichmuller G divided by gamma G. So this is the Teichmuller space that we discussed. Yeah. This space is contractible, and actually, as I said, is homeomorphic to an open ball in Euclidean space. DG. G on these two. Now I'm assuming G is bigger than equal to. Right. Okay. So as an exercise, I mean, so proving this is a bit complicated, but as an exercise, I want you to show that actually all complex structures on sigma G defined in this sense, this is a nice space, right? All tensor fields of this type. It's a nice topological space. This is contractible. So this is a good exercise. So complex structures on G. G is a contractible space. Okay. This you can do using the fact that if you have, for example, you have to relate this to metrics in some sense. You have to find some real metric. And if you have two metrics, any two metrics can be connected by a class of metrics. Actually, by interpolation. T plus G1 plus 1 minus TG2. Do this. Okay. So, because of this, then, now what we want to prove is this Euler, not Euler, I mean Harer-Zagier theorem. Okay, so let me before doing that, let me say this. So by using a suitable cell complex, we'll show that this takes next lecture. We'll show that now this mapping class group gamma 1G actually now, okay, I write it as gamma G gamma 1 has a finite cohomological dimension and has an Euler characteristic as finite cohomological dimension and as yeah, this was okay. Hi. Yeah. So, okay, so I did not discuss the case of positive n. Now here I'm introducing n. But this story that I did here, you can modify a little bit by including an n. There's a similar story, but it's a bit because you have now to take care of mark points also. Once you do that, then you have this, now this one, and then the Harer-Zagier theorem that we want to prove. Okay, is that actually this number G1 is equal to minus the Bernoulli number, I believe B2G divided by UG. This is the where B2 where Pn is the Bernoulli number, sequence of Bernoulli numbers. Right. Bn. And this is Bernoulli numbers. So these are have the generating series e to the x minus 1 equal to sum Bn over n factorial x to the n and yeah. This is the Bernoulli number connection. And because this guy now, so Mg1 is equal to this contractible space, this is Tausch-Euler space, right? Divided by gamma G1. Computing this Euler characteristic means that you're computing Euler characteristic of this system. So this Harer-Zagier, you can say that they are actually computing Euler characteristic of the moduli space of curves. So chi of Mg1 actually equal to negative d2 over G, right? So this was one of the first results about cohomology of this very complicated, mysterious space. But then there were a lot of results about it that was found. Some of it by physicists actually, Witten, for example, had this about it, and then so on. Okay, it's still going on. Okay. So this we'll do. We need 2 hours to finish that. But what I want to do in the remainder of today's lecture is to justify why this dimension here is actually why you get where you get this number 3g minus 3, where this comes from. I mean, why you have so many possibilities of complex structures, right? Because if I give you if I hand you one of these surfaces, sigma g, you will be in trouble even defining one complex structure. It's not clear. How would you do that? Yeah. So, and so there are many ways to see that. One very nice way is actually to use something called uniformization theorem. Okay. So basically this section I can say this is the heuristic count of dimension in G. It is heuristic only, but but there are a lot of theorems. So it is based on something, the famous theorem called uniformization theorem. So this uniformization theorem for Riemann surfaces, it says that any simply connected Riemann surface, any simply connected Riemann surface is of one of the following three types. The following three types. I mean, okay, the first one is that it's either complex plane, isomorphic as a Riemann surface to the complex plane, or is isomorphic to the upper half plane H, or is isomorphic to Riemann sphere. So this is Riemann sphere. This is Poincaré upper half plane. Poincaré upper half. And this is, of course, good old complex plane. Of course, notice topologically C and H are the same, even smoothly they are the same, but not holomorphically, as we discussed, because of Liouville's theorem. And this is, of course, even topologically different from this. So these three classes are mutually exclusive. They are not isomorphic to each other. But the result says that actually any simply connected Riemann surface is isomorphic to one of these three. And this is a very hard theorem, extremely hard theorem. But there are many proofs, I mean, several proofs at least. So now let's see what kind of information this is we can use in order to use it towards counting this dimension of Mg. Okay. So now let us take a Riemann surface. So now let X. Oh, okay, yeah. Now something I need to know about these things. By the way, there is a result in complex analysis that what result in complex analysis this should remind you, or would remind you of. One of the mapping results in complex analysis, which is kind of a grandfather of this. This is Riemann mapping theorem, right? The Riemann mapping theorem says that any simply connected domain in R, in C, I mean, is either C or is isomorphic complex-wise to the upper half plane. It's one of these two things, right? So, but this is much, much more general because you are not assuming you are inside C. You're assuming you have a Riemann surface, abstractly defined. Yet you show that there is this trichotomy. So this is quite powerful result, but it's a generalization, vast generalization of Riemann mapping theorem. Okay, but another thing from complex analysis you learn is, at least I hope you did, is that what is automorphism group of C? By automorphism, I mean the set of all complex isomorphisms of C. What is that? Do you know that group? Do you remember? So if you want to set up all bijections of C, which are holomorphic, and then would have holomorphic inputs. Okay, so this is something that it can be done in undergraduate complex analysis, and it's always done. So this is like the set of all AZ plus B things, A and B belonging to C, and A different from 0. This is just affine transformations of the complex plane. This is the only thing that's possible. I mean, you can imagine if you have something like order 2, you would have 2 zeros. So this kind of violates injectivity, for example. You can sense. Okay, so what is automorphism of H? Yeah, that's even more interesting. This is the group PSL2R, which is the group of all real matrices where these are real numbers. They are allowed to be real numbers. A, B, C, D, belonging to R. And you divide it by, so this is up to here is just SL2R. When I put P here, it means that the projective version of this, it means that I divide by the center of this group, which is plus minus identity. Divided by plus minus identity. This is the center of this group. Okay. Yeah. And the action is by Mobius transformations again, like the way we did with SL to Z action with the open of plane. And this one, on the orbital of CP1 of the sphere, Riemann sphere, you remember what it is?
Is it just the rotation group? Or I guess that would be for S2, but
Yeah, for S2, rotations would do, they are isometries, but they are hardly complex analytic.
yeah, they have the fixed points and the
And also fixed. But it's really the set of all, so this is, let me put it this way, is SL2C. Now you allow complex numbers, but it acts by, so this is the set of all, so the all A, B, C, D again, such that A, B, C, D. Now you're allowed to be complex numbers, but still you want the determinant to be 1. And now the action here, so we just see CP1 as C union infinity. And if you have a Z here, under one of these things, again, is a Mobius action, but it's on the spherical Mobius action. So there's a over CZ. Okay, so for these 3 simply connected Riemann surfaces, the only ones in the world that we have. This is an amazing result. Anytime you look at it, you have to wonder. I mean, it's such a beautiful thing. It looks like there are so many possibilities, but there are only 3 actually. It's like 3 gems of Riemann surface theory. But it's good to know the symmetric groups. So the symmetric complex or holomorphic symmetric groups are this. So the reason I mentioned this is because I'm going to use this now. So now imagine you have a Riemann surface of genus G belonging to 2. So let X be a closed Riemann surface of genus G belonging to 2. Now let X tilde be the universal cover of X. Okay, so if you have any reasonable topological space, doesn't have to be manifold or smooth or anything like that, just mildly reasonable, very, very mildly reasonable. you can always construct this universal cover. So this universal cover is contractible, and the fundamental group here acts on this by these monoclonic transformations for any x0 belonging to x. You can look at I1 of x at x0. So it acts on by deck transformations on x tilde. By so-called deck transformations. So if you have any G here, you just get something. G goes from x tilde to x tilde. This is pi. This is pi, and this is x. This diagonal commutes of deck transformations, and gives us a actually representation, and is faithful. In fact, this is faithful representation of pi 1 into the group of deck transformations of x tilde. So this is a completely topological story. However, since x is a Riemann surface, x tilde is also a Riemann surface. You can lift complex structure from x to x tilde. Because I mean, this x tilde is like a bunch of pancakes putting over each other, okay? So complex structure, so, and this G acts holomorphically. Okay. So now the question is, what is pi 1 of Riemann surface of genus G, right? Well, this is something you do in algebraic topology. So it's a standard result that phi 1 of this group, no, this is space, phi 1 of G handles is actually equal to the group generated by two G generators, A1, B1, B2, B2, AG, BG, and then there is only one relation between them, which is the product of commutators is also is 1. So this is product of commutators equal to 1. I equal to 1 to G. Now, what are these commutators? These commutators basically you can take a fixed point x0 here. Here, this is x0. And these commutators, you can just do the following. For example, around this, you can go here. And around this, you can go here. For each of these holes, you create a loop. You go around it like this, and then you go around it like this. You do it for all loops, but you always come back to the same point. And then you can show that there is no other relation except this. But this means the commutator of xy basically, by definition, is x y, x inverse y inverse. So this is the multiplicative commutator of things inside the. Okay. So if you have a Riemann surface of genus G, then pi 1 of the sigma G acts in the automorphism group of this x tilde, right? So now we have to decide what are the possibilities. Automorphisms of x tilde, we know what they are. It's either a z plus b, So this cannot hold such a thing. Or SL2C, again, cannot have such things. The only possibility is to be H. Given the list of automorphisms of C or H tilde, you conclude that H tilde is actually H, the upper half plane. So it's here. Right. So look at there. So, and in this case, we know that automorphisms of H is PSL2R, right? Right. So we've got a map now from pi 1 of sigma G to PSL2R. So this is a faithful representation, and its image, let's call it gamma. Or gamma is not a good thing. Maybe the image is a subgroup. So we get a subgroup. Subgroup. So let me call it gamma inside KSL2R, such that H divided by gamma is isomorphic to X, which is this Riemann surface we're starting. Right? Because this is a very general story here, as we discussed even in the last lecture. X actually is isomorphic to X tilde divided by this action of the pi 1, divided by image of pi 1, under this monodromy representation of this action. Take transformations, which is the same thing here. So this gives me this one. Now, so we have to address now, we are going to finish in 5 minutes, but we have now to address the following question. For what subgroups of gamma, so this is now a very important question. For what subgroup of gamma subgroups gamma of PSL2R H mod gamma is a closed, and of course a smooth without singularity closed Riemann surface. Such groups is completely known. These are the groups called Fuchsian groups, and these are indeed the groups that all elements of the group except identity are hyperbolic. So let me give you this definition. An element G belonging to PSL2R is called hyperbolic. G different from identity. is called hyperbolic. If absolute value of trace of G is bigger than 2. Well, you see, this G is, of course, of the form is a matrix, right? G is a matrix A, B, C, D, which is defined up to plus minus 1. And absolute value of trace of G is that absolute value of A plus B must be bigger than 2. So there is a condition purely in terms of this matrix. All elements of this subgroup must be of this form, must have this property. And yeah. Okay, so I think I better stop now because it's been going on for quite some time. To actually proving the count, showing that it's 3G minus 3 is reasonable, we don't need more than 20 minutes, so we can just do it next lecture. Yeah, so now, and also I want to define this Poincare metric on this because it's quite related to Riemannian metric structure on H, which is the Poincare metric. But this I think we deserve some rest now. Any questions or?
So I guess when we multiply the commutators of the generators, we
Yeah.
then get a 4G gone that glues. But I guess we only need 2G, but because we have the inverses, then that's where it's normally the 4G gone. That's the genus G, but
yeah, I know your
but 2G
4G
still
gun.
works.
Yeah, you use those 4G guns to construct actually Riemann surfaces of genus G using this disk model of the Poincare disk model of hyperbolic geometry. Yeah, which is same as this upper half plane, but working for polygons is better to work with the disk. Although I mean that's here is yeah, it's similar. Yeah, I think it's related to this story, but here we have really
It's just the 2G generators. So it's
yeah. These are the 2G generators, AI and BI. So
it's just
uh-huh.
oh yeah, I guess just with the 4G gone, it's easier to imagine the gluing, but 2G gone, it does enough
Yeah, you see, I'm not
topologically.
using any polygon here now.
Yeah.
Yeah. So yeah, but it's what you're saying is also relevant to the story. But here, this computation is purely algebraic topology. We can just so how do you prove this using Van Kampen, Seifert-Van Kampen theorem? When you have two topological spaces, you know the homotopy, the fundamental group of each. When you glue them, you can compute the fundamental group of the amalgamation of the two and something like that. And this computation comes. It's a very nice result, of course. Yeah. Yeah. So, but I could not show why 3G minus 3 appears, or actually in the real case, 6G minus 6 appears. But this is the beginning of the story, so that's very nice. A nice intuitive way of understanding the dimension of modular space. Only intuitively, yeah. Which can be made more rigorous. So far, everything I said is completely rigorous. At the end, there is a little bit of dimension counting in the sense of Riemann, actually. Yeah. Okay, so it looks like there are no other questions. Okay, so have a wonderful weekend, and I see you next week.